Okay, good afternoon. Working? No, not sure. Use this one too. Yes, good afternoon. So yesterday was a bit of a revision for all the row and column operation stuff, inverses of matrices, and reduced row echelon form, all of that stuff anyway. So hopefully that's now, you know that very well. Then we talked a little bit about internal and external direct sums, which can be a tiny bit confusing, but important. And today, now that we understand internal and external direct sums, we can state and prove the so-called rank nullity theorem, which is something you probably saw last year as well. But it's one of the fundamental results for finite dimensional operators on finite dimensional spaces. In fact, the finite dimensionalness isn't even important. So we'll state it in general here. Okay, so the rank nullity theorem, we've got a linear transformation between two F vector spaces. And rank nullity tells you that, that V is isomorphic to the kernel, external direct sum, the image. But think about what's going on here. So the kernel is a subspace of V. The image is a subspace of W. So indeed that has to be an external direct sum in general. In the special case when W actually equals V, then the image is also a subspace of V. And in that case, you have to regard this as an external direct sum, because there's no reason why kernels and images, when it's a map from V to V, why they're going to be intersecting only at 0. Okay, we'll say something about that later. But anyway, let's prove this first, and then we'll look at consequences. Okay, so the way this goes, well, the kernel is a subspace of V, and so we'll extend that by putting in a complementary subspace. So let U be a complementary subspace. So that means V is kernel plus U, and that guy there is an internal direct sum. And yeah, so a bit the difference with external and internal, another difference I guess, is on the left-hand screen there, we really have to write V as isomorphic to this thing, because it's not equal to this thing, because one of them lives in V and the other half lives in W. Whereas here, this is actually equals. This is all living inside the ambient space V. We've got this direct sum. And what it means to say direct sum, that means, to say that U is a complementary subspace, the kernel of theta intersected U is 0. So the key things are that the kernel of theta intersected U is just 0, and V is the sum of the two things. Okay, and our aim now is going to be to show that U is isomorphic to the image of theta. And then we've got the theorem. So we'll show that U is isomorphic to the image of theta. So how does that work? We have to find an isomorphism. Well, there's not much going on except for this linear transformation theta. So we'll use theta to construct the isomorphism. And we'll look at what's called the restriction. So that's theta. The notation is often with a little bar here and U. That means theta restricted to U, and it just means restricting the domain of theta. So theta was a function that had domain V, but now I consider it just a function on the smaller domain U. And I'm going to be a bit more specific with my codomain. Earlier the codomain was just W, but I'm going to specify image of theta now. That's certainly fine. Okay. So let's draw a little picture of what's going on here, just so we all understand. Here was V, here was W somewhere over here. We had our map theta taking us from V to W. Theta maybe mapped this all down. It wasn't necessarily surjective. Maybe I'll make that a little bit bigger. That in there is the image of theta. So theta's going across there. Somewhere inside V, we've got U. There it is there, let's say. And we're considering theta just restricted to U. And the claim is that that's actually an isomorphism. So I'm trying to show that this map from here to here actually is an isomorphism. In principle, I mean, before I know that, this would perhaps go to a smaller, I mean, it wouldn't necessarily be surjective. It might go to here or something. But we're going to say that doesn't happen. So firstly, let's check surjective, I guess. Theta restricted to U is surjective. For if we have a W in the image, I have to find a U in U such that theta of U equals W. Well, to be in the image, I'm theta of something, but something in V. So W is theta of V. That's the definition of being in the image. And then, natural enough, write V in terms of the internal direct sum. So that's with X in the kernel and U in the U in U. I'll just phrase that there. All right, so then the point is theta of U is, what's theta of U? Theta of U is theta of V minus theta of X, but X is in the kernel, so that's theta of V, which is W. All right, so it's indeed surjective. Okay. And now to check injective. Maybe make a bit more space there. it's, well, theta of u, I mean, to say that, it's obvious, really, because to say that u is in the kernel of this linear operator means that theta of u is 0, so u is actually in the kernel of theta. But it's also in u, because it's in the domain, but that equals 0. As u is complementary. So the kernel is trivial, so it's injective. Well, not trivial, equals 0, so hence injective. All right. So theta u is an isomorphism. So v, which equaled kernel of theta plus u. I'll just give a tiny bit more space again. Is isomorphic to kernel of theta plus image of theta, where sort of on the left-hand side there we're internal direct sum, and on the right-hand side external. Okay, so that's the idea. You might want to check this little conclusion here that's saying that if you've got an internal direct sum like this and another space which is isomorphic to u, then it's isomorphic as an external direct sum like that. But that's just right out as a natural proof. A good exercise. All right. And just to remark what I was saying earlier, so in that special case when our theta is actually an endomorphism, that's an endomorphism. Then the kernel and the image are both subspaces of V, so it's certainly a bit confusing. Well, internal and external direct sums would mean quite different things there. So it's not necessarily true that the image and the kernel intersect only at 0. So that kernel plus image has to be regarded as external. So for an example, consider theta from R2 to R2 with, so for example, theta of x equals 0, 1, 0, 0, I think works. So in this case, the kernel of theta is, well, the things that are killed are everything in this band just by solving the equations. Right, that's right, isn't it? Yep, y equals 0 and x is free. And the image, well, that's the column space of our matrix A. Call this A here. And that's also 1, 0. Okay, so in this case, certainly the image and the kernel intersect. Well, they're in fact the same. Okay. Well, so that's why I carried on a bit about internal and external things yesterday, so that we don't get confused by such situations. Anyone still confused? Or is it all right? All right, so that's the rank nullity theorem, a very simple proof. But it's got lots of consequences. This consequence is often actually called the rank nullity theorem, but the thing we wrote down earlier is a bit better because it doesn't have the finite dimensional parts tucked in here. But now we're going to, yeah, there's these old-fashioned names. Rank we talked about the other day. That's the dimension of, well, if we're talking about rank of a matrix, it's the dimension of the column space, but the column space is just the image of that matrix when you consider it as a linear operator. So for a linear transformation, so for a linear transformation, the rank of theta is, by definition, the dimension of the image. Okay, so this is a definition. And the nullity is it's a kind of stupid word, I think, but it's the dimension of the kernel. It's an old-fashioned word, but it still gets used. Anyway, but that's why it's called rank nullity theorem, because it links those two things together. And so if we have a linear transformation from V to W, if we know that the dimension of V is finite, that's important for this consequence, then in fact the rank and the nullity are both finite as well. I mean, the nullity has to be finite because it's a subspace of the of V, dimension of the subspace of V, but in particular we'll get that the dimension of the image is also finite, but that's sort of clear enough as well. And moreover, they add up to the dimension of V. But this we've already done. This is just that the dimension of V equals the dimension, well, it's just because V, I'll write it this way, sorry. V is isomorphic to kernel plus image. So that says dimension of V equals, indeed, rank plus nullity. Okay, so it's sort of the same thing, but just stating it with dimensions. Yeah.
So that means the dimension of a transformation from a finite dimensional vector space to an infinite dimensional vector space can't ever be subjective.
Yeah, that's right. The image. So let's think of that another way. So we don't really need the rank nullity theorem to see that. So let's say we've got a linear transformation from a finite dimensional space V to some infinite dimensional space. So we just don't care what's over here. But remember, how do we see what the image is? Well, we can take a basis for V, and now the image of theta is now spanned by the images of those basis vectors. So it's if this was n-dimensional, the image is spanned by n vectors, or maybe fewer even, but in particular it has dimension less than or equal to n. So the image of a linear transformation is always in dimension less than or equal to the dimension of the domain, is what we're seeing. And you see that by taking a basis, looking at its image, that spans the image. I mean, the images of those basis vectors, and there's n basis vectors, so at most dimension n for the image. Yeah, that's right. So in particular, exactly what you said, if that was finite dimensional and that was infinite dimensional, or even just bigger dimensional than this, strictly bigger dimensional than V, then you can't be surjective. Yeah, that's right. It's some kind of, I mean, these vector spaces, if we're working over an infinite field, like the real numbers, all these vector spaces are infinite sets. But it's something like the analogy with maps between finite sets. If you have a finite set mapping across to a strictly larger finite set, or larger set anyway, strictly more elements, then you can't be surjective. It's the same idea. Yep.
Wait, you just said this is like a corollary, but you said like sometimes the theorem stated like this. Is this one and the original one, are they like equivalent basically?
Sort of, but not quite, because this one insists on saying that the dimension's finite. But if you knew the dimension was finite and you say that these two things these dimensions add up, remember we had a theorem or a proposition lemma or something that said being an external direct sum was equivalent to having the dimensions add up, or equivalent to all this kind of stuff. Or we said that, so the fact that these two dimensions add up to this means whatever these two spaces were, if you take the external direct sum of whatever those spaces were, in this case the kernel and the image, it'll be isomorphic to this guy over here, because it'll be of the correct dimension. Okay, so take any two F vector spaces, take the external direct sum, the dimension of that external direct sum is the sum of the two individual dimensions. Yeah.
So if you
Well, that's if we're insisting on finite dimensional V's here, I mean, first for okay, so you said the word continuous, but continuous is going to insist that we need to work over the reals or the complex numbers or something, first of all, as our vector space. In this course, we don't really look at the analytical aspects on top of, we're looking at vector spaces in general, in particular over arbitrary fields. When you're working over the reals and the complex numbers, you can start looking at continuity aspects. Any linear map from a finite dimensional space in the domain is necessarily going to be continuous, but maybe what you're getting at, they do exist when you have an infinite dimensional space here. You can make discontinuous linear functions from the vector space to just the ground field, which will be the real numbers. But that's, yeah, we don't talk about that in this course. That's functional analysis, where you start putting the two concepts of linear algebra and like convergence, infinite series, all that kind of stuff, continuity, you put those two things together. But in doing so, you absolutely have to fix your field to be the reals or the complexes because, well, you know, you need to have that measure of distance and so on. All right, all good? Yeah, it's a good course, functional analysis. It's quite nice. Taught that a long time ago, but still sort of remember it. All right, here's another good corollary that maybe we'll prove two ways, in fact, once with the rank nullity theorem and once just by hand. So this is also the analogue of having a map between two finite sets of the same size. Then if it's injective, it's necessarily surjective, and if it's surjective, it's necessarily injective. So it's like a common thing when you're counting things, that if you know that both sets have the finite same number of elements, if you've got an injective thing, then it's surjective and vice versa. Okay? So that isomorphism, or bijection, is the same as either of its two constituent pieces, let's say. The same happens for vector spaces, where dimension now plays the role of the finiteness. So we need our two vector spaces to be finite dimensional and of the same dimension. That's the important part here. Then you're an isomorphism if and only if you're injective, if and only if you're surjective. I mean, so all of these are equivalent. That's what we're saying here. So that's quite useful, but don't start using this statement when the dimension of V and W aren't the same, because then it's just stupid. Okay. Certainly not true then. But this the one-line proof is from the rank nullity theorem, just saying, where am I here? Just using, well, let's just write it out. So we've got the dimension of V equals dimension of the image, or kernel, I think I normally write first, plus dimension of the image. And what you have to think of, so if you were injective and if you were surjective, that's just sort of, well, I should probably write words instead, but I'm just going to draw a little picture to see what's going on here. So if we were injective, then we know that the kernel is just the zero vector space, so this is zero dimensional. Okay, and this one's n, or whatever, let's say. And that forces this to be n, which means that it's all of W. Okay, the image is all of W. And similarly down here, if we were surjective, that means that our image is everything is W, which had the same dimension as V, so n, let's say. And then that forces, of course, this to be 0, which means you're injective. Okay, so injective implies surjective, surjective implies injective, so either one implies bijective. Yep.
So you can show all of them by showing that theta is an invertible matrix.
Or invertible linear operators, so you should be careful with matrix, but yeah, you could. But sort of to show it's invertible, I think you would probably be showing it's bijective, I guess. So probably it's still this same. Yeah, so like if you just know theta's injective, how are you going to say that it's invertible without just saying it's surjective and therefore invertible? Maybe. Yeah, but you're exactly right. Yeah, you're showing, yeah. There. Anyway, so it's nice. One-line proof with rank nullity theorem, or quite a picture. You can sort of see why it's true, hopefully. But just a remark: there's a perfectly good other proof of this, which is just as good. So what we really have to do is show that if we're injective, then we're necessarily surjective, and vice versa. So let's say, so what do we want to do? We want to take our take a basis for V, map it across to W, because we're assuming we're injective. So if we assume we're injective, then that linearly independent set, which was a basis as well, but linearly independent set remains linearly independent over in W. So that's something we proved, that if you're an injective map, then you map linearly independent sets to linearly independent sets. So we've got a linearly independent collection of vectors of the right size to be a basis, because the dimension of W is the same as V. So it is a basis. Okay, so that means, and since you're a basis, then you're a spanning set, so that means theta had to be surjective, because if you map, if you map a basis over here to a basis over here, you're surjective. And similarly, if you're surjective, then I guess we do something the same, where we take our basis for V, we send it across, it becomes a spanning set over there by the surjectivity assumption, but now we've got a spanning set with the right number of elements, so it's a basis. So actually, theta was injective as well, because it mapped linearly independent to linearly independent. Okay, that's the idea. So remark, a direct proof goes as follows. So theta inject. So let B be a basis. I don't really need it to be an ordered basis, but I'll keep with ordered bases, I guess. Basis of V. So 1, if theta is injective, then it implies that the set theta V1, theta of Vn is linearly independent in W. So that these are things from week, last week, I guess, week 3, Monday's lecture of week 3. And that means that it's a basis. That's by dimension. So that's because dimension of V, we have to use somewhere, of course, that fact. And so that says theta is surjective. And that's again because it's mapping, because of the spanning property now. Maps basis to spanning set. Well, I don't know, maps a basis to a basis. In fact, I don't really have, it's not really that it's surjective, it's actually because in the statement in week 3, it's just theta is an isomorphism if and only if it maps a basis to a basis. And that's what we've said, it maps a basis to a basis. So that's again week 3. Theta maps basis to basis if and only if it's an isomorphism. And similarly, if theta is surjective, then it maps this our basis to a spanning set, not necessarily linearly independent at this stage. That's again week 3. But now it's a spanning set of the right size. And so it's, again, mapping a basis to a basis. So theta is an isomorphism. Okay, so it's perfectly good proof as well, of course. Okay, so you don't know. It's not like you absolutely need the rank nullity theorem for that statement. Good. Just a comment. The above, so by the above, I mean this property that if you've got a map going between two, let's say the same space even, so that we know it's got the same dimensions. Let's have an endomorphism now. So in finite dimensions, an endomorphism will be injective if and only if it's surjective. That's what we've just proved in finite dimensions. But now let's take infinite dimensions and endomorphisms L and R. So these guys get used a bit for counterexamples. First one is called the left shift operator, like you've just booted x1 off. So remember what seq f is, just all these infinite, x1, x2, x3, x4, dot, 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 with all of those xi's being in the field f, with the natural scalar multiplication and vector addition. Left shift is just we throw away x1 and shift everyone across to the left. Right shift, we move everyone to the right. We have to choose what to put here, but to be a linear function, a linear transformation, that has to be 0. And there's no other option of what we put there. So we put 0 there to make it linear. So these are two linear things. And yeah, so these give examples of one of them is injective but not surjective, and the other one is surjective but not injective. Let's now that out. So L is certainly surjective. That's obvious. I mean, map, you get every sequence popping up on the right-hand side. That's because of the trick that, if you've got an infinite sequence, then chopping off the first thing, that's still an infinite sequence. You get all infinite sequences there. I mean, so something clearly happening about infinite dimensions that you couldn't do in finite dimensions. But it's obviously not injective. For example, it maps, the 1, 0, 0, 0, 0, 0, that guy gets mapped to 0. Okay. So it maps a non-zero thing to 0. And on the other hand, R is, that one's injective. That's sort of obvious too. Like if you've got two things that match up, then all of their components will have to match up. But it's certainly not surjective because you're forced to always have 0 in the first component in the image. So anyway, finite dimensions are important. But you would expect that anyway, because a map from Z to itself, integers to itself, you could have certainly an injective map, like the one that maps 0 to 2 and 1 to 4, and just like doubling everything. Let's take natural numbers. Natural numbers to natural numbers, where you just double everything. That's injective, but it's obviously not surjective, because you miss all the odd things. So anyway, you would expect this. It shouldn't be a surprise. But important to say. Any questions about that? Yeah, so coming up to our next example, maybe we could just say here, maybe we'll just continue with this one for a second. So note also, if I do LR, is that the one I want to do? So that's first doing the right shift, because it's composition. So first doing right shift and then moving them back again. That's the identity. So that's a case where you've got these, so sort of somehow L is a left inverse, so to speak, of R. R is a right inverse of L. But neither are invertible because they each fail to be either injective or surjective. So they're certainly not invertible. And also RL is not the identity. What does RL do? So if you first shift across to the left, you throw away x1, and then you shift back again, well, where the x1 used to be, you've got a 0. So that's not the identity. That's now the map that just kills the first coordinate. That's not the identity. So that illustrates that at least in infinite dimensional spaces, the left and right-sidedness of matrix inverses looks important. But in fact, for matrices, because we're in finite dimensions when we're talking about matrices, it's not important. So the following are all equivalent. A is invertible with inverse B, AB equals the identity, or BA equals the identity. So you just have to check one of the sides. So clearly that's not true in infinite dimensions by that little example we just did. So let's prove that one. So that's also, we'll prove it with the rank nullity theorem. Where have I got my... Here it is. This is the way I want to prove it, I think. Okay, so let's prove that. Proof. Well, first of all, it's clear. Clearly, A being invertible with inverse B, by definition, implies 2 and 3. So we have to worry about the other directions. So let's assume 2, and there's a symmetry with 3. So AB equals I. And the little trick, I guess, is we'll regard A not as a matrix, but as a linear transformation. But I'll call it theta of A just to try to be clear. That's now from Fn to Fn. Be the linear transformation theta A of V equals AV. Well, then the condition that we got, that AB equals the identity, tells me something. It tells me either A is injective or surjective. I have to think about which one, but then I'll know the other one for sure by the rank nullity theorem. But it tells me that we're surjective. So then theta of A is surjective, and that's because if I have a V, anything in the codomain, that's saying in the codomain, is I times V, but that's A times some other thing, BV. i.e. theta A of BV is V. So I'm certainly surjective, and hence injective. By rank nullity. So it's invertible. Specifically, just because we're still on the, for this last little corollary, really worried a bit about inverses of matrices and stuff, we'll check that the inverse really is like the B, the matrix B. That's what we should check. So theta A inverse of W is, well, what does it mean to be the inverse of a function? This is the unique V with AV equals W, and that's BW. Okay, because BW has that property and it has to be unique by the inject, because we know we're injective and surjective. So this is theta B of W, let's say. So just to say one thing, how do we get both sides? Because we've got inverses of functions. Oh, whoops. I don't need that because we discussed that earlier. How do I get rid of it? Delete. So then, since theta A inverse composed with theta A equals the identity map on V. And that's also theta A composed with theta A inverse. That's about something about functions. I mean, the inverse of functions satisfies that. That F composed with G and G composed with F are the identities on the domain or codomain, respectively, but here the domain and codomain are the same thing. And so that gives B, A equals A, B equals I. And similarly, assume 3 and ... exercise. Same deal, you'll get, if you assume 3, which was the BA equals I, then you'll get that A is injective, and then you'll get it surjective by rank nullity, and then you can play around with it again. Okay, so it's something you have to do at one stage in your life to check lefts and rights. It's a little bit fiddly. One last thing, I've got still got some minutes. There's one other quite striking consequence, I would say. It says that any linear transformation from vector space V to vector space W, you can pick bases in V and W such that your matrix for theta with respect to these choices of bases is like super, super simple, like as simple as you could possibly imagine. And here's the corollary here, here's the statement. So we've got an n-dimensional V and an m-dimensional W, linear transformation between them. Then you can pick a basis of V and a basis of W such that the matrix representation of theta with respect to A and B is, this is the n minus k identity matrix. One's down the diagonal for n minus k, and then everywhere else is zeros, and k is the dimension of the kernel. So it's kind of a very, very simple way of writing the matrix. I'll make a comment about that in a second, because we're going to, in a few weeks, we're going to talk about Jordan normal form, which is much harder somehow, and we put a lot more effort into it. And I'll try to explain why, while this is impressive somehow, it's not that useful, this decomposition, this expression here. Anyway, let's just prove it first, and then we'll make the comments. So it's using the rank nullity theorem. They're already defined, so I don't have to suppose. We've already called dimension of V as n and W as m. So following the proof of rank nullity theorem, let V1 up to Vk be a basis of the kernel. And remember, in the proof, we then took a complementary subspace to the kernel. So I'll make a basis that extends that. So it's all about choosing this basis. The first k terms are in the kernel. And the rest are just chosen. They will span a complementary subspace. That will be the thing I called U earlier. Lots of choices, of course. That's a basis of V. So then theta of these things over here. Remember that we showed in the proof of the rank nullity theorem that theta restricted to U was an isomorphism to the image. So this now becomes a basis of the image of theta. So that was because, so that's from the proof, as theta restricted to U as a map from U to the image of theta was an isomorphism. All right, so now write I just give these names. Theta of v k plus 1. I think I swapped them around, the order around a little bit. Oh no, don't. Just shift it down. I think if I got my indexes right, this is Wn minus k. Now I extend that further more to a basis of W. So that's a basis of the image of theta, which is a subspace of W. And we can just extend that to a basis of W using basis extension theorem. So we've got W1 up to Wn minus k, and then we just whatever we need. Basis of W now. Then theta AB as the required form. Let's check. So we'll call this, this basis is my basis A. This one's my basis B. Because what do I have to do? I have to look at what theta of VI. Theta of VI, well, the first k of them are in the kernel, so they're killed. Oh, sorry, I've got to swap things around to get it being a bit... So A I'll take as written there. B, sorry, to get the identity up the top, I probably should have put it down the bottom. As a required form, where I'm going to change B. B is now defined to be Vk plus 1 up to Vn, so the second part of the basis first, and then V1 up to Vk. Because then, so just to explain why, because theta of Vi, if I'm in this first chunk here, theta of Vi, well, that's just exactly that. That's Wi, in fact. That's if 1 is, well, it's a bit confusing. So maybe I have to, my indexes are wrong. Let me just illustrate by example. So theta of Vk plus 1 is W1. Theta of Vk plus 2 is W2, etc., etc. That says we're looking like the identity matrix there in our, because our first column, second column, third column are given by these these coefficients we're getting. But then when we get to theta of V1, well, that's in the kernel, so that's 0. And we're 0 evermore. So that says we're identity for the first bit, and then columns of zeros after that. Quick remark. So any questions about that? It's just about picking bases. But just a quick comment. I'll write something down later, but let's just use some words. So the point of, if we're talking about endomorphisms from V to V, then both the V basis and the W basis would both be bases of V. That's fine. But the problem is then if we want to look at endomorphisms, often what we want to do is compose them. And if we want to compose them, we can use our rule that theta, so if we have different bases A, B, and C, well, sorry, theta 1 composed with theta 2 in the basis AC equals theta 1 in the basis AB times theta 2 in the basis BC. But the point is, so okay, that we proved this formula. So the way the matrix multiplication works, the bases have to align like this. But the point is, if we want to use the same matrix representation for the theta 1 and theta 2, so same bases, then we need these two bases to be the same. So A, B, and C are all going to have to be the same thing. So that's a much more severe restriction. So if we want to use matrix multiplication to do composition or high powers of a, like powers of a linear operator or something, we need to pick the same basis in the V domain and the V codomain to make it practical. So we'd want same basis in V and V. That one's domain, that one's codomain. And that's a much more complicated question to try to, so the question for week 9, I think it'll be, is to try to find the nicest way of choosing a basis of V, in both the same basis in the domain and codomain, such that the representation of theta is as simple as possible in terms of you can then make calculations with it. But that's much harder than this thing we did over there. Okay, is that clear enough? We'll talk about it again when we come to it. Okay, good. See you for the practice class.
不是讨论，真不是讨论，开数的都是擦掉的。高中说这是真讲，没有，那不是讨论，真不是讨论，是真不会。上节课要是上节课要是没有你，我就真的不知道他讲。今天开完那个，是因为太快了，他一般会做第二次。哦。就是刚刚那个棒棒糖的那个，对，对，对，无语，拜拜。我打卡，正好正好是。因为我搭他的这个全套，就是有，也不是，其实很沙了。那大概是。